Okay, anyways, welcome everyone. Let's start. So, what if I told you that a single concept inspired by how humans focus their attention could revolutionize the field of NLP or natural language processing? What if I told you that this concept, when it was encapsulated into a model called the transformer, it could outperform all the models across a bunch of tasks in machine translation, and that further set the stage or the foundation for all the state of the art models we see today? So, welcome everyone. Today we are going to dive into the groundbreaking paper "Attention is All You Need" by Google. They published this back in 2017, but we are still seeing the effects of this paper in the entire ML, AI, deep learning, and across the industry domain, transforming the entire idea across the world. So, a bit about myself to start with. Currently, I am a software engineer at Meta. I work in the PyTorch org, specifically helping them develop all the pre-processing pipelines for recommendation systems. I'm heavily interested in learning more about GPU and CPU perf optimization. This is a lot of work when you talk about like really huge models across ads or across any kind of recommendation systems. You need to understand how and where the perf gains can be found. Prior to my work at Meta, I used to work on ML acceleration at AWS, specifically on the Inferentia and Trainium hardware. And I got my graduate degree from UCLA and did my undergrad from VNIT back in India. So in my free time, you can find me playing ping pong, reading books, or playing FIFA 23. I haven't updated to FIFA 24 because there's almost no difference yet. Okay, so for all the discussions we are having today, I'm assuming that you have some basic understanding of machine learning and deep learning. You also understand what are vectors and how we usually represent features or any kinds of input into this embedding representation. These are some basic concepts which I'm assuming you already know because we have a lot of ground to cover, so we won't be able to start everything. And yeah, I'm hoping that we have this discussions to be interactive and get involvement from everyone. All right. So to start with, I'll just spend like the first 10 minutes giving you some background on sequence to sequence models. What are recurrent neural networks? What were their limitations? And how was this transformer model born? And then we'll talk about the transformer model itself, its architecture, what kind of modules we have inside it. And then we'll talk about the main crux of this entire paper, which is this self-attention mechanism. We'll spend a majority of time on the self-attention mechanism so that we can gain a mindset on how to think about this concept. We are not going to like look into the maths of it all. It's very complicated for a 1 hour talk, but we'll talk about all the concepts. Then we'll quickly like run through the training process, what kind of data set they used, did they have any kind of regularization, what kind of hardware or like what was the schedule for the training. We'll quickly run through the experiments and results. These are stale results now because they are back from 2017, but it's still worth it to like look at them right now. We'll end the talk by talking about how this model impacted the entire industry, and we can then open the floor for some Q&A. Okay, I think this animation is in reverse. Okay, to start with, what are sequence to sequence models? So they are type of a deep learning model that converts an input sequence from one domain, like sentences in English, to sequences in another domain. Like it can be like French, German, Hindi, Marathi, or any other language. So usually sequence to sequence models are used for use cases like machine translation, speech recognition, text summarization. And the sequence to sequence models back in the day, like back in 2017, they were usually recurrent neural networks, what we call RNN. So main takeaway from all these discussions is you can think of this as a black box right now. We just want to focus on the idea that you get like an input sequence and each input token from the sequence is processed one at a time. So the model will output one token at a time given this input sequence. So how do they go about it? Let's look inside the sequence to sequence model. So if we peek inside, if you look at any kind of sequence-to-sequence model, any RNN as well, it usually has two components. One is an encoder and the other is a decoder, as you can see. So what is the encoder doing over here? It's just taking all these input tokens from the input sequence, processing each of them, and then generating a context vector. So these things might appear very confusing right now, but I'll assure you that once we discuss more about this, it will make sense. So what is a context vector? Example, I have a sentence, what am I doing here? So how does a machine or this specific algorithm understand what are we going to talk about? Like how does it understand, okay, what am I doing here? What does this sentence represent? So there's a mechanism using which the encoder will convert all of this text into a representation, usually embedding, which is called the context vector. So the decoder uses this context vector in combination with the inputs to generate like one output in the sequence, one at a time. So it's a time step based process. It takes one input at a time. The encoder processes all of them, then generates a common context vector, and then the decoder processes it one input token at a time. Now let's unroll the model for neural machine translation, which is like the heavy use case for RNNs. So let's assume we have got three encoder RNNs in the encoding stage and three decoder RNNs in the decoding stage. Okay, I'll wait for the GIF to restart. Okay. So encoder RNN takes the first token once, it creates a hidden state. Then it takes the second token plus the previous hidden state, generates hidden state 2. Then the third token, and then it generates an overall hidden state which it feeds to the RNN. Now, what is the decoder RNN doing? It's just taking this final hidden state and any context vectors it has generated at the end. It's not using the hidden states from the previous encoder RNN steps. It's just using the final time step and feeding it into the decoder RNN. And then one output token is generated one at a time. So uh, if everyone is following, can I get a thumbs up from everyone? Okay, great. If you have any questions, please feel free to write them on the chat.
Actually, can you talk a bit about the final stage when it passes from the final context to decoder? So it doesn't use the hidden layer, right? It only use the final representation to pass from encoder to decoder. Is that correct?
Yeah. So it will only use the final hidden state over here. We are not like this entire model, like any kind of NNN, it was not using the hidden state from previous steps. That was one of the limitations which we will talk about. Furthermore, like if you generate like one output token, the next step usually takes this output token as input along with the previous hidden state generated by the decoder. So each of these states is being fed to the next step along with the previously generated output. Like that's the idea. So we don't want to dive too deep into RNNs because we have a lot of ground to cover in the transformer itself, but we'll talk about the limitations and what are the main blocks here.
I see. Yes, that's another a related question as well. I think Madhu has how is the context different than the hidden state, the hidden layer. I think that's what it means.
It's actually not different. It's quite similar. It's just something which is being passed from the encoder to the decoder. So we call it the context vector. But essentially, each of these states is generating a encoding of any kind of input which it has been fed. So the first step only knows about the first token in your input sequence, while when you convert the last token in your input sequence, it is having a context around the entire, like each of these tokens. There is still some limitations to this hidden state or this context, which we'll talk about next. Hope that helps.
So I have one question. Like in the encoding stage, how many encoder RNN do we have? Like as you said, it is taking one token at a time. So like how many encoder RNNs will be there in that case?
Got it. So let me show you a better figure which helps you understand. So usually any kind of RNN, if you have to visualize it, It's
Mhm.
usually just a simple black box. You can just think of this A as your RNN, and you have this input token at time step t called as xt. Now, if I have the sentence, what am I doing? So the first time token at say time type token 0, at time step 0, it would be what? Now you input this token to the model, it
Mhm.
generates hidden state, and then it also generate doing the decoding stage. Sorry, it's not doing the decoding stage, but it's feeding back the output of this hidden state back to the next time step. So when you have, say, the second word, what am, when it's processing am, it's also taking the previous hidden state and any information which the previous time step has generated. So basically, when you unroll it, you will have as many hidden states as there are input tokens.
Okay. Okay.
So that's a limiting factor of RNNs, like we'll talk about them. So basically, for each of these time steps, the RNN, if we unroll it, it's generating a hidden state per time step, that is per token. So what am I doing? Each of these tokens would generate their own hidden state, which is quite limiting in a way. We'll talk about why. So basically, when you talk about, say, this hidden state 3, and you have got some input tokens in the like earlier in the network, this hidden state 3 can't actually gain context on long range dependencies. So say you
Hmm.
have a sentence which is like 1,000 word long, you can't actually take the context from the sentence which is earlier because the RNN, it has some limitations which we are going to talk about. So main idea is vanishing and exploding gradients. So how does the model actually learn? We have a simple algorithm, not simple actually, but the gradient descent algorithm, where during the backprop step, we need to translate all the gradients across the network. But due to this vanishing and exploding gradients, what happens is during the model training process, these weights either become very small, like they either vanish, so there's no learning, or they either explode. Explode as in they are so huge that the learning goes haywire, like it's not valuable. So it makes the training of the network across like long sequence lengths very hard. Furthermore, as you saw over here, the main idea is RNNs struggle with capturing long range dependencies in a sequence. That means that if there's any significant time gap between the relevant information, example, I had a sentence saying, um, I am driving a car in San Francisco heading towards, say, Portland. Now, driving towards San Francisco, heading towards Portland, all of these contexts for a RNN, it's very difficult if you have got a sequence which is of a large number of input tokens. So this relevant information can't be usefully contextualized by the RNN. Furthermore, since we are doing all of these computations sequentially as in one input token is processed one at a time, you can't actually parallelize all of these steps, which leads to like slower training times compared to models where all of the all of the elements can be processed together. And finally, since we are producing one hidden state per input token, that means you are going to require a really huge memory for a long sequence because each of these tokens is going to generate this hidden state. Does it make sense till now? Do you have any questions?
So I have a question.
Yeah,
In a traditional RNN, whether it's identity or predicting the next word, the back propagation happens pretty much like, that step 1 or step 2, and the embedding layer is learned. In case of sequence to sequence, when does the back propagation happens? When the decoder starts predicting, and then it uh, uh, unrolls back the gradient, and that's how it learns.
correct. So all
Okay.
of the gradient would only start after the model has made its first incorrect prediction. So for the model to actually learn, it has to make some mistakes, and then based on the loss function between your prediction and what actual target sequence we are aiming for, that's where the back propagation starts. So when your model has to go back from your decoder output 2 back to your encoder's weights, it can't translate all these gradients because of these issues with vanishing and exploding gradients. So there were some networks called like LSTM, long short-term memory, and all these other variations which tried to solve these problems. They kind of solved the vanishing gradients, but they were not able to solve the exploding gradients, or they were able to get the long range dependencies. But again, the sequence length was quite limited. They couldn't go beyond a certain sequence length.
Okay,
Uh,
perfect.
okay. So
Thank you.
Yep.
I have a question here. When you're talking about the sequence length, that they were not able to go beyond the sequence length, so do you mean that deep? Do we have like neurons in the deep learning network? So they could not extend the number of neurons. This is what you mean by when you are trying to say that they were not able to extend it after a certain limitation.
So they can actually extend the network to as many steps as they want. But the idea is the hidden state at the end, say what we saw over here. 1 minute. So the hidden state at the end, even if you have got say 1,000 time steps, this hidden state is only being fed from the final stage, like the last encoder RNN.
Mhm.
Like the unrolled RNN, only the final stage is being fed to the decoder. That means it can't hold all this information because your hidden state also has a dimension of the embedding to follow. Like the hidden
Okay.
state can't be of arbitrary dimension, but it has some dimension, say 128 by 256. Now you can't encode everything, all the input sequences and all the context in your input, the relationship between all these words in a in just one representation. Like that was the main idea with or the issue with RNNs.
Okay. Okay. I got it. Thank you.
Okay, so having discussed all these limitations, how do we solve for these? Of course, we are talking about the transformer model, so that's the thing we are going to use. So, so the transformer model, let's think about this as a black box for now. We will slowly unwrap the onion and look inside, like what's happening inside. So again, a transformer model, it's taking an input sequence, say in English, and it's generating an output sequence in French. So why are we talking about neural machine translation over and over again? Like there are so many other tasks, but the original transformer paper, it only focused on two tasks, which was English to German translation and English to French. So that's going to be our mode of discussion for most of our presentation today. Okay, let's look inside the transformer model. So what is it is made of? Again, it is made of encoders and decoders. So you have got a stack of 6 encoders. That's what the paper uses, and a stack of 6 decoders. So you feed all your input sequences, tokenized and converted into embeddings to these encoders. These encoders do some magic inside, and then they feed their context vectors or hidden states or whatever they are generating back to the decoder. Let's clarify this even more, like what is it exactly doing. So as we previously saw, encoder generates a hidden state, it feeds it to encoder 2, and so on and so forth until you reach hidden state 6. Now this again, hidden state 6 would be fed into the decoder. Okay. So overall, until now, we understand, okay, we have a stack of 6 encoders and decoders. Each encoder maintains a hidden state. Only the final state is being passed to the decoder. Okay, but doesn't this sound like RNNs again? If you're only going to pass one hidden state, this is quite limiting, right? So how do we solve for this? So what if we could pass in all the hidden states, like this hidden state 1, hidden state 2, 3, 4, 5, 6, feed everything to the decoder in some representation, which helps the model remember the dependencies between, say, input sequence token 1 and token 1000. How can it learn these dependencies between the word? So that's what the paper suggests. You take all the hidden states, do some kind of transformation, softmax, and generate like a attention-based context vector, and then feed that to the decoder. So I'm not assuming that you all understand what is an attention-based context vector. That's the point of the discussion. But we'll dive into this in the next slide. So let's zoom into the encoder and decoder next. So what is the encoder? Encoder is just made up of, at the high level, two blocks. One is the self-attention mechanism and a feed-forward neural network. So we'll talk about the self-attention mechanism, which is the highlight of this paper. But for the feed-forward network, I hope you all know, like, feed-forward network is just a simple neural network, like a linear neural network. But in this case, it is a point-wise neural network. When I say point-wise, what do I mean? So say your self-attention mechanism, I have a sentence, what am I doing here? So a self-attention mechanism takes in all these input tokens at once, but your feed-forward neural network takes the output of the self-attention per token and then does feed forward, or like a simple linear pass per token. That's the difference. So idea is that the self-attention mechanism requires a data dependency on all of your input sequences, or like all of the tokens in your input sequence. But the feed forward network can only act independently on one token at a time. That means that even if we can't parallelize this part of it, we still can parallelize, or like the smaller chunks of the feed forward or the linear layers can be accelerated using, say, parallel processing or GPU. Like that's the main benefit of the transformer paper. Then we have the decoder. So again, the decoder also has some kind of self-attention. It's a bit different than the encoder, but still a bit different. We'll talk about it. Then we have encoder decoder attention. So there are some context vectors which the encoder generates and which are fed to the decoder. So this helps the decoder understand, okay, on which parts of the generated context vectors from the encoder I should focus on. That's the main idea. The encoder again has some feed-forward networks and followed by some linear layers and softmax layers, which finally gives you some probability score or the final output, which is representing a word. Okay, let's zoom into it even more. So as we saw, you have got two words. Let's start simple. So you have got two words, thinking machines. Now the model itself, it can't actually act on text, as we know. It requires a representation of these words into some mathematical form. So in case of, say, deep learning or all this NLP space, these numbers are called embeddings. So what are embeddings? They are simply some kind of matrices or some kind of vectors which are representing a word and its context. So these embeddings are well known. Like there are models already doing this called like word to vec, wall to vec. We have got glove embeddings, all these different embeddings. So we are not too concerned about that. So we get all these input tokens tokenized and then converted into these embeddings. So what do I mean by tokenized? You have got the sentence, what am I doing here? So we'll split it into individual words. What am I doing? And each of these words would be converted into an embedding. Okay, so we are clear so far. Then we have your encoder one. So we previously saw the self-attention mechanism and the feed forward, like point-wise feed forward. As I told you, each of these tokens would be going through the feed forward network point-wise. It's not sharing the computation between these two. Okay. So what is the self-attention mechanism? That's going to be for later. What is residual addition and with normalization? Okay. So residual addition, what it's doing is it's just finding a way to get more representation of the same inputs, but at various granularities. So example, when you feed these input embeddings to the encoder, it would have some set of numbers. Then once it goes through the self-attention mechanism, it will have some other set of numbers based on what this function is doing. Self-attention, each of these blocks is what? It's just a function taking in some vectors or some embeddings and giving out some other vectors or embeddings. Now residual addition with normalization is just taking the values before the self-attention and adding them with the values after self-attention and then doing some normalization step. That's the main idea. Then we have the point-wise feed-forward network. So, okay, this will take an individual. So X1 would be transformed into some transformed embedding or vector called, say, X1 dash. Now that would be fed through the feed forward network. Same for x2 dash. And then we would have again residual addition with normalization. So for our understanding, we are just thinking in terms of two encoders. The real paper has 6 encoders, as we saw. And for the decoder side, what do we do? So what are these previous outputs? So as I told you, the model will generate some outputs initially, which may or may not be right, but there are still some kind of embedding representation. Can we use those? Yeah, like we are using them over here. That's the idea. So the decoder will take any previous output embeddings, again feed them through some special self-attention layer, have residual addition with normalization, followed by this encoder decoder attention, again some residual addition, feed forward network, again residual addition. So it's kind of repetitive, but that's the main idea here. And the main idea is the self-attention mechanism and the encoder decoder attention. So followed by the decoder one, we'll have another decoder two. Similar to this, we'll have like till decoder 6. At the end, we have a fully connected linear layer, which simply gives you some form of logits. Logits are simply probability scores across a distribution for each of the tokens. And then the softmax layer helps you convert these logits or these probability scores for each of these words into actual words. So it's not actually giving you the word itself, but it is telling you, okay, which of this word appears most likely. So looking at all the components we saw till now, we have got the encoder and decoder stacks. Great. We understand like what the overall structure looks like at 1x zoom. Then we have got the self-attention mechanism, which we did not talk about. We'll talk about it next. Then we have the residual connections. Okay, let me connect my charger. Actually, it's going to turn off. Just a minute. I think I'll need to get my charger. Hold on for a second. Okay, we are back. Okay, so what are residual connections? As we saw, see you've got any input x to some layer, then the layer performs some transform f of x, these two layers. So what is residual connection doing? It's just taking the same input x and adding it with the output of these two layers. So you get the idea. That's the overall idea of the residual connection. There's nothing more complicated. Then we also spoke about point-wise feed-forward networks. Point-wise feed-forward networks are really simple. Like they're just taking one input token at a time and doing like a feed-forward network. It's nothing complicated as this paper or this name suggests. Point-wise here only represents that it's only acting on one token at a time instead of how the self-attention will act on the entire input sequence at once. So let's focus on self-attention mechanism. Can I get a thumbs up if everyone is following? If you have any questions?
Yes, I have a question. Can I ask
Yeah, sure.
now? Yeah, so I understood, the identity, the residual connection, but then the question is why it's needed.
So the same idea with why we are taking context vectors from different hidden states. So idea with residual connection is that when you do all of these transforms, like say self-attention or any kind of deep layer, like deep learning layer or neural network layer you add, you lose some information in the input sequence. Now to gain back context or like information on the same granularity as you had before, you add the same input embedding back to the output of the transformation. So this f of x gives you some new dimensions of understanding the same input, but at the same time, it's still losing out some information which the original embedding was representing. So it's just adding like more information to your learning.
But if you have a layer, I mean, for example, I think this skip connection comes from the computer vision where you have hundreds of layers like ResNet 150, and then you don't lose the information. In that case, it makes sense. But here, if you have only 6 encoded block, which is not too many, if I compare with 150,
Right.
so does it make sense to have this skip connection here? I mean, that's what I'm not able to understand. I mean, it's 6 encoded is not too many compared to 150, right?
Yeah, I mean, the number might appear very misdirecting when we look at convolution neural networks and all these NLP models. But the main idea is that even within a single encoder stage, there are so many computations happening. Like if we look at the self-attention mechanism next, but the way these self-attention context vectors are generated, all these query key and value vectors, how they are generated, they are not that straightforward. So we are still losing all the positional information on our input. So example, in this case, it matters in case of textual information, what order in which the inputs are fed. Like in case of RNNs, we had like time steps. In case of the transformer layer, like transformer, these inputs are encoded with something called time encoding. Like they're trying to encode these vectors with some information showing that, okay, x1 appears at an earlier time step compared to x2. So all that information might not be carried forward in the self-attention layer. That's why we need.
But that is captured within position encoding, right? That's what position encoding is for.
Exactly. So that's the positional encoding why we are using it again. I mean, it's just a redundancy. They might have gotten results without this as well, but looks like they got better results with the residual connection. That's the idea.
Mhm.
I mean, there's
I have
no, the thing with such experiments is that they don't plan it out before writing all these papers. They are doing some experiments, they try out multiple variations, and then once they find the best results, that's how they try to justify why it's useful. So we don't fully understand everything, why these networks are built this way.
Can I ask you a question?
Yeah.
Yeah, I might be a follow-up on the gentleman's question before me, but like, why f of x plus x? Why not f of x plus 500x, right? What? It feels to me f of x and x are not scaled the same way, right? So it seems really weird to me. You just add those two things. Can you explain that? Why is there not a weight in between to try to at least learn how they scale?
So they are already transformed. Like over here, I'm assuming they are in the same dimension, but the actual model won't be just adding them up. So example, your f of x is say 1 into 128 dimension vector. Your x is just 1 into 24. So we'll need to find a way to translate this into the same format. All of this is handled by broadcasting in most of these networks. So they're just broadcasting the dimensions or the maximum dimension between the two vectors to be the same.
Yeah, I was not talking about the dimension. I was thinking the magnitude of the vectors, right? Why would we expect f of x or x? Like one could absolutely dominate the other. And so I don't see the intuition x plus f of x seems very arbitrary to me. I get the idea of reinjecting information. It's just the scaling
Yeah.
between the two is odd. Seems like arbitrary. Do you have any thoughts about this?
So they are not actually adding the same values. If we understand this, all the embeddings which we are getting over here, so the embeddings over here, all are normalized around 0. If you see how embeddings are built, same with the self-attention mechanism, all are normalized around 0 because of the softmax layer we have inside, or how these scores are calculated. We'll look inside
Oh,
self-attention next, but they are not different scales. Like, of course, they won't
okay.
do something which is so like so clearly incorrect. So the idea is that the scales for both of these are quite similar. That's why they can get away with just adding them and then normalizing them. Like that's the idea with normalization.
Okay. Thank you.
Yeah. I have a question about computation. Can go back to the previous slide.
Yeah.
Yes. Yes. So this slide here. So remember on the RNN side, when you feed, so try to understand the input and output of each layer. So the input is basically each token, right? It go like one token at a time. But for the this transformer model, you take all the token and you feed directly into the self attention layer and do parallel computation there, right? And then upward. So do we need a 6th layer of encoder?
Yeah.
Yeah. So what's the reason for having six? What's the benefit of having six encoder?
So honestly, I read the paper and I read a bunch of other articles as well why they did it. So the
Yeah.
authors themselves agree that there's no real reason why they chose six. It could be 10, it could be 20. But since you have some limits to how much compute resources you can use, how many GPUs, all these P100 GPUs they are using, how many GPUs you can use, and what kind of benefit you are getting by adding more encoders. So in case of their experiments, they saw that six encoders is just enough. It's not too much and it's not too little. Just giving them the best performance on all these translation tasks which they were hoping for. So they chose six. There's no, there's no like just one reason why they chose six.
I see. Well, actually, another question is, so go back to the side. So before, like on the RNN side, let's say after all the pass through all the encoder, the final context basically comprised of all the token, like one hidden layer. But in this case, the hidden layer between encoder 1 and 2 basically already comprise all the context of all the previous token, right? And you take that and you feed into another encoder to get another representation. And at the end, you have like 6 different hidden layers that all have different meanings of all the words that you feed in. And then you feed it into the decoder. Is that correct understanding?
If I may add to that, I think we are stepping ourselves forward. Let's look into Mandar's presentation of key, query, and value vector. I think things would be much easier and simpler. That's my recommendation.
Yeah, I agree. Like we have like so many things to talk about. We can definitely
Yeah.
discuss them. But once we look at how this self-attention mechanism uses these,
Like,
we'll make it.
exactly.
Okay.
Yeah, thanks Tuan for the question. So okay, let's look at the self-attention mechanism. So basically, say you have the sentence, the animal didn't cross the street because it was too tired. So how do we, like for humans, it's very easy to understand what it refers to in the sentence. It could refer to the street or it could refer to the animal. But for the transformer model to figure this out, we need to use the self-attention mechanism. Like that's the idea. It can disambiguate it being referred to the animal rather than the street. How does it do it? So basically, let's tokenize all these words. The animal didn't cross the street because it was too tired. Now, when you are processing each of these tokens in the self-attention mechanism, it's trying to recognize, okay, what do I want to focus on? So when we read the sentence, we instinctively know that, okay, when it's talking about it, it's the animal. But for the model to learn this, how does it do? So it's trying to score all other words in the input sequence in context to how important it is for this specific word. That's the main idea. So over here, we have just weighted the scores for each of these words in the sentence, and we can see the animal has the highest weighting. That's the output of self-attention, but we'll dive into it next. So let's quickly run through the self-attention scoring. I think this will help clarify most of the things. We are going to like not spend too much time on this since we only have some 15 minutes remaining, like actually 10 minutes remaining if we want to also do some Q&A. Okay, so we have got this input sequence thinking machines. We convert them into embeddings. Then we generate some vectors called query, key, and value. Now you might think, what are these arbitrary vectors? So these 3 input vectors are generated in the encoder itself, and we generate them using 3 matrices called WQ, WK, WV. These 3 matrices are instead generated during the training process. So it might appear all easy, like why, like how is it generated, where is it generated? But during the training process itself, there is a parallel task going on to generate these 3 arbitrary. They are arbitrary. We can't, like the authors call these queries, keys, and values. But for the model itself, they don't make any sense. They are just 3 matrices randomly initialized initially. But as the model trains, they are learning some values which the authors are using to generate this queries, key, and value matrices. So simply, it's just a multiplication of your input embedding with the WQ vector to generate the query vector, with the WK to generate the key vector, and the WV vector to generate the values vector. Now, once you have this, how do we use this? How do we use these values? So the model needs to learn how to use these abstractions to score each of the words. Now, in the self-attention mechanism, let's say that you are processing one word at a time. The actual model actually does all of this in a metrized form. It won't do like row by row computation. It's doing all of this in a matrix multiplication for perf. But for our understanding, we are going to look at only one word at a time. So let's say you are processing the word thinking. So how is the score defined? You simply multiply the query vector with the key vector for this one. You get like say 112. Now for finding the score of the word thinking in reference to machines, you just multiply the query vector for thinking along with the key vector for machines. So that gives you a score. So it's simply a dot product between, or like element wise multiplication between the query and the key vector. That's giving you a score. Once you have the score, we do some form of normalization. We can ignore this. This is not too important. D in this case is just the dimension of your key vector. So you just, in the paper, it's D, like it's 8 because their dimension of their key vector was 64. So they got like, okay, 14 and 12. So once you have these values, we need to convert them into some form such that words which are highly relevant stay intact, but any kind of irrelevant word which are like it, the, is, and they are not that important, right? They don't need that much of importance when you are talking about a word like thinking or machines. So softmax is helping you moving all these values, like the important values will move closer to 1, and any irrelevant word or some minor values which are smaller than the highest value, they'll move closer to 0. The idea is if you have got like 1,000 words over here, the sum of all the softmax output would sum up to 1. In this case, since we are only talking about 2, this 0.88 and 0.12 are summing up to 1. Okay, so we have until this point. Now we multiply the value vector in this case with the softmax vector. This will help dilute the values or the values representing thinking into some form which also encodes the importance of that word. Like softmax already gave you a number close to 1 for words which are important to say thinking, and words which are less important to thinking get a lower score in the same context. So you multiply both of these to get like a weighted value vector. Then you sum these up individually. So when I say sum these up, this V vector is generated for all the words in reference to thinking. This Z2 vector is generated for all the words in reference to machines. So that's the idea. Like Z1 is what the encoder or like the self-attention layer would output as an input to the feed-forward layer. So the actual paper does all of these calculations in matrix form, as I mentioned, for improved performance. The real model has multiple attention heads. So when I say multiple attention heads, what do I mean? So similar to how we generated these 3 matrices during training, the actual model will actually generate 8 or 6. I don't remember how many attention heads they had. I think they have 8. So they generate 8 such sets of matrices and generate 8 such set of query, key, and value vector. And similarly, such Z1 vectors are also generated as a set of 8 in the actual model. So why do they do this? It helps the model focus on different positions in the sequence. Plus, it's also providing an additional representation subspace for the attention layer to work on. If you're like transferring it to like different representations across different ways, these scorings and outputs won't remain same because your model or any case machine learning is not an accurate science, it's a heuristic. So each of these matrices would be quite different. So you generate all these 8 sets of Z1, find a way to convert them into a common representation and then feed it to the feed forward network. Okay, so I think we have covered until this part. Is everyone following? Are we doing good? I know like there are some things which will still remain unclear, but the idea with this discussion is to just help us gain that concept and then you can dive into it.
I had
Yeah,
a
I have a
question.
quick question.
Yeah, Joydeep, go ahead.
Yeah, so let's say we have Jack and Jill went up the hill. That's only our word in the entire universe.
Yeah.
Now, when we are randomly initializing these three matrices and adding multiple layers, over the period of time when it encounters more and more such sentences which are meaningful to each other, wouldn't all these layers of self uh, attention would merge or converge to similar weights? And my question is, how is the linear transformation happening if your basic input is the same set of context word or context token?
So to answer your first question, it won't exactly be the same because in each of the input sequence, the self-attention is focusing on that input sequence dimension. Example, in this case, you have got like 5 words. Now, the importance of machines to thinking in this sentence would be different compared to the importance of machines in, say, a sentence which is 1,000 words long.
Ah, okay, got it. Okay.
And for
Um,
the feed-forward question, like the linear transformation, what was the question again? I forgot.
No, I think you answered my question. I was trying to get the intuition how adding multiple headed self-attention helps the linear transformation and learns the meaning of the word. I think you answered it pretty well because the words are going to appear in different text in different attention numbers or scale dot product. So
Yeah.
the linear transformation will help the model understand the entire vocabulary or entire corpus it is trying to learn from. So no, I think you answered my question. Thank you.
So what I'll do is I'll want everyone to hold on to your questions. We'll quickly walk through a bunch of these slides we have, and then we can have a Q&A at the end since we only have 10 minutes. Other folks will drop out otherwise. I hope that's okay. Can I get a thumbs up? That sounds okay.
Yeah.
Okay. So I think we covered most of this self-attention, normalization, and all this residual connection. Now the decoder part, it's quite similar to the self-attention which we had in the encoder. There's only one variation. In the encoder, you are looking at all the input tokens in the input sequence, but in case of the decoder, it does something called masking. So it doesn't look at the inputs in the future. It only looks at the input at the current time step and focuses on that. So I'm not going to talk too much about the decoder because it's quite simple actually. If you look at the paper, the main idea is the self-attention layer. And the encoder decoder attention, what is this? So at the end of the encoder 6, like the 6th encoder in the stack, it generates a set of two, I think context and key vectors, which is feeding it into the encoder decoder attention. So what is this doing? So this one was helping us focus on the input embeddings, the input tokens. This encoder decoder attention is helping the decoder focus on a specific part of the encoder's output. So it's a bit different. This is focusing, or the self-attention is focusing on the input embeddings, whereas the encoder decoder attention is focusing on specific components of the encoder's output. Like that's the overall idea. Okay, I think we have spoken about self-attention now. What else is remaining? Okay, I think one thing we did not talk about is positional encoding. So as somebody else also brought this up, we need to pass in a way to remember at what time step each of these inputs belongs to. So we simply insert a time signal which adds a distance between different words in the sequence. So what is this time signal? So this T1 is some representation which is helping you move your input at time step 1 away, a bit away from your input at time step 2. So say you had got the same two words at position 1 and 5. Your time positional encoding would help you disambiguate their embedding representation because you are encoding their position in the sequence using some representation. So you embed their signal with that, like embedding their representation with a time signal. So why are we doing all of this? So during the self-attention layer, when you're generating all this query, key, and value vectors, you need their embedding vectors to be far off from each other, so that self-attention can actually understand, okay, the word what am I doing here, and then the word what at the start of the sentence compared to the word what appearing say 1,000 time steps down the line, both are different. So this positional encoding simply helps with that. So any input you have to your network over here, these are already like over here. I did not add that block, but this is adding the positional encoding over here before feeding it to the self-attention layer. Okay, we have spoken about self-attention, positional encoding. I think the embedding and softmax components are remaining. Let's quickly talk about them. So say in your decoder, you get your decoder output. So all of this stack, we are focusing on this part before the fully connected layer. So you did all this computation, you found a representation of your input sequence, which is going to convert into your output in some form of decoder output. This is an embedding. You follow it up by a linear layer. Linear layer is simply again a simple linear neural network, which will convert your decoder output into a logit. So what is a logit? Logit is just a probability distribution across your vocabulary size, telling you, okay, how much importance do I think this word has, or how much does this decoder output represent what? How much this decoder output represents and all these words in your vocabulary would get one probability score. Now the softmax layer will help you distill this probability score even further. It will move the words which are higher in probability closer to 1 and move out any other probability scores closer to 0. Then you simply do a Rmax value, like Rmax of this output of softmax, and do a lookup index. Like it just gives you a lookup index for your entire vocabulary. So based on this index, you came up that, okay, my current word is am. When you map back to your vocabulary, that's the basic idea. I know I'm not covering all of this in detail because of what amount of time we have. So okay, congratulations everyone. You mostly understand what transformers do. Cheers to everyone. I think you'll still need to spend some time understanding what are the internals and understanding the maths behind it, which requires you to like get your hands dirty and actually write some code. That's the best way to learn for such complicated scenarios. Let's quickly talk about the training process. What training data did they use? So they use the workshop on machine translation 2014 English to German dataset, which had like 4.5 million sentence pairs. So when I say sentence pairs, 4.5 million sentences in English followed by their pairs in German. Similar to that, they had 36 million sentences for English to French. And for the training batch is just one set, or like how much data does one epoch of the training constitute. So there are like 25,000 source tokens and 25,000 target tokens. So what are these tokens? So the sentence, what am I doing? So what am I doing? Each of these words, when they are split from the entire sentence, we can call them a token. So their training batch actually consists, like one training batch is consisting of 25,000 source tokens. So you can imagine like what they did over there. And if you think what's happening today, this appears very simple, but it wasn't back in 2017. So they trained their model on 8 NVIDIA P100 GPUs for 12 hours for the base model and 3.5 days for the big model. And of course, since we are talking about GPUs, yeah, we should just look at it. For the regularization, they use residual dropout and label smoothing. These techniques themselves are like residual dropout is not that difficult to understand, but I think it would be better if we discuss or learn about this after this talk. So what were their experiments? They did 2 tasks, English to German, English to French. They used this data set, which we know. So the transformer model, when compared against the best previously reported scores, like convolutional sequence-to-sequence models, recurrent neural network, they compared it against that. In terms of results, it beat all the previous models on these 2 tasks. On the English to German score, it achieved a blue score of 28.4. Now you might think, what is blue? It's like bilingual evaluation understudy score. It's a way, like it's a metric in natural language processing, which is used to evaluate quality of machine generated output against some golden reference translation they have. So you can see it handily beat all other kinds of models and at the same time not taking up too much of compute. So you could parallelize the feed pointer feed forward network. The attention mechanism could be split onto a different machine. All of these things could not happen with RNN. That was the main takeaway of this model. So what kind of impact this model had on the industry? It single-handedly bootstrapped the language modeling space. I shouldn't have included LLM over here, but the main idea is that all the current LLMs, they are based on the models built on top of transformers. So we had the transformer model, which is like a stack of encoders and decoders. Then OpenAI came up with a transformer, which was only the encoder, similar to what BERT was also doing. Like BERT was only a encoder. So they thought that, okay, if decoder is helping us translate the output of the encoder into some other language, what if we just remove the decoder and fit in any custom task on top of your encoder? So what they were interested in were just some representation of their input sequence into this context and query or all these vectors. And then they added some, say, classification task on top of it, a simple logistic regression model on top of it to convert this BERT or the same transformer encoder into a, say, a Q&A model. So this architecture where you're using just the encoder of the model is what's driving all these GPT-2, GPT-3 and all these other models. So basically, after this model came out, it has been like almost 7 years now, and still the same architecture is being used across all these use cases. OpenAI came up with ChatGPT 2 years ago now, like 1.5 years. Google had Bard AI, now they are calling it. I don't think it's the same thing. They are coming up with Gemini now. Anthropic has Claude 2, and now Meta is focusing on a lot of all this Llama series of models. So I can't say like it's just the transformer which is enabling this. There are other mechanisms like RHLF, like taking all this feedback from the user and improving it. All this mechanism which OpenAI added for Instruct GPT. All of this is building on top of each other. So you might think, okay, this is just limited to text, but honestly, it's not. You are seeing a lot of speech-to-speech communication problems as well, like the Pi bot. If you haven't tried it, I would recommend you to try it just as soon as possible today. It's a free app, both on Android and iOS. Now, Alexa is also using the transformer model. ChatGPT's voice mode is also using transformer model. And I'm not hoping, but I still think that we are headed to a future where we'll have people talking to AI bots and AI agents throughout the day, similar to what was happening in EX Machina and her in the near future. I hope not soon, but it's going to happen. So better for us to be prepared and actually understand how it works so that we don't get fooled easily. Okay, I think that's most of my discussion. Let's now open up the floor for some questions. I will have another interesting paper reading next month. If you have any suggestions or any questions, feel free to ping me on LinkedIn or any other question. Like, let's talk about it.
I have a question.
Yeah.
Why is there a key and value tensor or matrix, or because if the key value is asking, if the if query vector is asking I have this to offer, and then the key value asks like, yeah, you are related to me. What does the value you think is doing? I don't get it. Like I have read that it's like what it actually offers, but I also read somewhere that key and value are also almost the same thing. So like what's going on there? Like I have read like both of those things.
So the thing is, when you think about any of these models and what these researchers are doing, any of the abstractions which they say, they are giving it a name. It by itself is not representing anything special. They generated these three matrices, WQ, WK, and V, and generated some vectors using them. Now, the way they are using it in their model is what's driving the name. But by itself, they are not representing anything unique. if you think about it, they are just abstractions which the model authors have called key value and query.
Is there
Can you
any
hear
way
me?
to?
Yep.
I think the reason the value is there, because once you generate the dot product of key and value, sorry, key and query, it uses that information to reorder the value vector, because value vector originally starts with the same positional encoding. So it uses some math to reorder the value, reorder the sequence of that vector. Somewhere I read it. So there is a significance of that in the whole architecture. Reorders the value of the, sorry, not the value, reorders the position of the value vector, which actually is nothing but stack of the vectors, then the encoding of each of these words that you stack it up in based on your context length.
Interesting. Yeah, I need to read about
Interesting.
it. I'm not
I
aware
have
of it.
already read somewhere that the value vector actually contains the positional embedding, but the key value does not. So, and that's one of the difference. I have
Yeah,
also
but when
another
you
question.
bring them together, it reorders that. You're right. The value vector is original positional encoding. The key and query also start with original position encoding, but it goes in a linear transformation, which is a scale dot product. And the output of that is, again, I think it does some matrix multiplication, but the reason it does that is to reorder that positional encoding and brings up uh, some of those rows that might be more relevant or more you want to get more attention out of it. And probably not be able to explain exactly, but I know it reorders the positional encoding of the value vector after the math is complete.
Hmm. I have another question. Is there any way to understand some way of understanding in natural language what the key vector or a particular key vector or a particular value vector is? Like what does that mean? For example, you can, if you have a context vector, you can put it in a decoder to understand like what that context vector actually means. Is there any way to understand what like a particular word that is generating a particular key vector? Like what's the relationship between them? Or it could be any value vector or query vector, it doesn't matter.
So you can actually visualize all of these things, but the interpretability of all of this is quite limiting. Like that's the issue with any of these deep neural networks. Like you can understand what these numbers are representing in relation to other query and key value vectors, but I don't think there's a way to absolutely get an understanding of what they are representing. That's the issue with what these embeddings and weights do. So I would say there's a there's a Harvard experiment, like not an experiment, but they have a repo where they have a illustrated transformer. What they did is they coded or they have inlined the entire paper with PyTorch code for each of these components. So if you walk through it, that will give you like a really intuitive understanding of how this looks in code, and maybe that helps you clarify it further.
You mentioned illustrated transformer by Harvard.
Let me say, no, the annotated transformer. Let me send a link in the chat. So they just walk through the paper and they write like code blocks for each of the components which the paper discusses. So if you read through it or even try to like code it along with the authors, that helps you clarify most of these things.
Okay, thank you.
Anyone else? Do you have any questions?
So I just read this, Mandar. The scores that comes out from the softmax function, the scale dot product, is used to create the weighted sum of the value vector. So that score that comes out, it used to, it's a basically a weighted sum. So, and the result of each word, which is combination of information from other word is in the sequence, is weighted by the relevance. So that's the use of the value vector. It reorders it based on the relevance, which is derived from the weighted score from the key value matrix that's coming out from the scale dot product.
Makes sense. So I think the softmax which we got of the score, when we multiplied with the value for individual vectors, we sum all of these value vectors which we have found for different words, and then that gives you the
The
weighted
weighted. Exactly. Yeah,
sum.
exactly.
Okay.
And also, is there any logic behind when you divide the dot product by square of the square root of the dimension of those vectors? Is
So
there
this
any
is
logic?
basically just for normalization. So they just found out, okay, what's the, so why do they do it? So the score, if you see, it's a dot product between the query and key vectors, right? So one of these dimensions is already similar to like the values. It's there's no logic to it if I think about it now. It's just a
Yeah, I
way.
mean, it seems like, to reduce, to avoid exploding gradient, maybe, I don't know. I mean, you just
Yeah, I mean, I don't know why
divide
they
by some.
started the dimension of the
No,
query.
yeah, you're right. So
It's
when
just
you multiply the dot product, sometimes the value can be too large or too small, and it's computationally not good. So in machine learning, we try to normalize, and same thing what softmax does, e to the power whatever m, then summation of e to the power. What it's doing is normalizing and bringing it to a same scale, which computationally is more efficient. There's nothing different in the math of it, but it's just computationally more efficient.
Yeah, I
to
mean,
do it.
yeah, that I understand. But again, why you divide by square root of the dimension? There are many ways, other ways also,
Oh,
right?
yeah, that's
I mean,
coming from the
that's what.
information theory. That's derived from information theory.
And what, I mean, what is the exact log? I mean, do you know the exact concept from the information
Yeah,
theory?
I don't remember, but it's coming from the information theory. So it might be able to
Basically,
Google and find that.
basically you need in order to be normalized, you have to have like mean zero and variance one. But if you take the dot product between the query and the values, so you have to divide actually by the square root of d, so that you again get the dot product as a normalized vector in terms of mean zero and variance one. So just to get the variance one for the dot product, you kind of need to divide by the dimension. And they did some ablation as well, where they did mention this fact that they have it's better to have a
Oh, okay.
variance.
Mhm.
Yeah,
Yeah.
exactly.
Yeah,
It's not the
yeah,
information
that's a
theory,
good
but
point.
rather it's just
Yeah,
from basic statistics. If you're adding
right.
n random numbers, and they are random, maybe they are like sampled from the normal distribution. And if n numbers are added, the standard deviation of the addition will scale with square root of the number of numbers, square root of d, that is. So if you divide it, you're
So,
basically dividing it by the standard deviation of that many numbers. So if the d model, if the dimensionality of that vector, let's say if it's quadrupled, then the standard deviation will grow by 2 times. You see what I'm saying?
hmm.
So if you divide it,
Yeah, so it's
bring
kind
it
of
to the unit.
similar to, right? It seems like kind of similar to how you find out z-score when you do
Yeah,
standard
yeah,
normal
yeah.
distribution.
Exactly.
Yeah.
Exactly.
Mhm.
Amazing. Thanks, Jaydeep, Anubhav, Bhaskar, and
It's a
Safka.
great discussion. Looking forward to the next one. And thank you again for your time to go over this on a weekend.
Yeah, definitely. I enjoyed it. Yeah, my first talk. So thanks everyone for attending.
Thank you.
Thank you so very much, everybody.
Thanks,
Thank you.